So anytime you have a conservation law, be it conservation of energy, conservation of mass, conservation of volume, whatever it is you want to think of as being conserved, charge, you're almost always going to end up with a differential equation. So a conservation law is almost always really somehow a differential equation. And here's one way to think about why. So if you're looking at some law of conservation of something, and I don't want to specify what it is that's being conserved, so I'll just use this generic term, stuff. So conservation of stuff. Then one way to write it, well, here's a simple way to write conservation of stuff. The rate of change in time of the amount of stuff equals 0. That would be a way of saying that stuff is conserved. The total amount of stuff does not change in time. But typically, what you have is not like a closed system, where it's just like, let me represent a closed system by this kind of box with stuff in it. Typically, you study a system in isolation, which is actually part of a larger system. So typically, it's not closed. There's ways for stuff to get in to your system and for stuff to get out. Then you wouldn't say that the rate of change of the amount of stuff is 0. No. Instead, you would express the fact that stuff is conserved like this. So you can think of conservation of stuff as saying the rate of change of the amount of stuff equals the rate at which the stuff is coming in, so whatever rate this arrow represents, minus the rate at which the stuff leaves. So this is some kind of differential equation, or at least it will be if you fill in, if there are some particular functions representing some parameters that you're trying to track in time, and if you can use those parameters to express the amounts of stuff and these rates, then this becomes a differential equation. So conservation laws are differential equations. Now, I want to look at a more specific example, and this is what your textbook author calls a chemostat. So imagine that you have a tank of liquid, and there's some chemical in there. So let's say let me put some input pipe and some output pipe. And there's some chemical in there, and the tank is full. Let's say it has volume V, is the number of cubic meters of liquid. Let's make it more specific. Let's say this is salt water. So cubic meters of salt water. Is V. And let's say water is flowing in at a certain rate and it's flowing out at a certain rate. And the water that's flowing in, the water that's flowing in also has some salt concentration to it, which might be different from the salt concentration in here. Then one interesting thing that you might try to follow using a differential equation is how does the salt concentration in here evolve in time, given certain fluid flow rate in and certain concentration of the salt water coming in, and given the flow rate out. So initially, at least for now, later in the course we'll make this more complicated, but for now, let's assume that this V is a constant. So the total volume of salt water here doesn't increase or decrease. To guarantee that, I need the flow rates of liquid in and out to be equal, so that the total volume of water here doesn't change. So assume that water is draining at a rate of Q, water flow rate volume per time, so Q cubic meters per minute. And let's say that it's coming in at the same rate, Q. So Q represents the fluid flow rate for fluid coming in and for fluid going out. And what's coming in exactly? Some kind of salt water from some reserve that you have elsewhere, and it has some concentration. Let's say the concentration is Cn. And what would be a good way of, a good unit for salt concentration? I guess mass of salt, so grams, per volume of water, so per cubic meter. So how many grams of salt there are in a cubic meter. I don't know if kilograms is a more reasonable unit. I don't really have a sense for how much these would be, but let's say here's the setup. Now, what's the concentration? This is an important part to reason through. What's the concentration of the water coming out? So in here, there's going to be a certain concentration, which can change in time. So let's call that C of T. This is gallons per meter cubed. So amount of salt, mass of salt per cubic meter of water. And I'm going to assume that this is one thing. There's one concentration in here. In reality, this is not such a good assumption. In reality, if something very salty is coming in here, then this area will be very salty, and it'll take time for it to spread out its saltiness to the rest of the tank, right? So you'll have less salty areas here, and then very salty areas here where the extremely salty water is coming in. But so it wouldn't make sense then to have this one number, C of T, represent the concentration overall in this whole tank. But let's assume that, kind of an ideal condition, that this tank is perfectly stirred, that it's perfectly mixed all the time. So whatever salt comes in instantly gets diffused throughout the entire tank evenly, so that there is one concentration that is the concentration throughout the tank, rather than concentration varying over space, over different places in the tank. Okay, so given that assumption, that the tank is perfectly stirred, what's the concentration of what's coming out? Well, it's the concentration in the tank. So what's coming out has concentration, whatever is C of T. Now, what law governs, C of T? How does C of T change in time? So, to get a law that governs how C of T changes in time, you can write down a conservation law. So require that salt be conserved, or something be conserved. So one thing you might think of is, I could require that volume be conserved. It should be, right? But that won't get you much. It is conserved simply because the flow rate in and the flow rate out are equal. What is interesting is that is what you get when you demand that the total amount of salt in the universe here, in this little universe, be conserved. Salt can never be created or destroyed. So let's write that down. So it should follow this template. Rate of change of the mass, the amount of salt, equals rate salt goes in minus rate salt goes out. So this is what we should end up with. All right, so what is the total mass of salt in the tank, first of all? So let's start with this. How many grams of salt are in the tank at any given time? Well, the tank contains C of T grams of salt per cubic meter, right? And the tank contains V cubic meters of liquid. So when you multiply these, that tells you how many grams of salt are in the tank. So that's what goes here. Okay. So I'm going to follow this template and then just continue to fill things in. I've now filled in this portion. So ddt of C of T times V equals, and now rate of salt in. So what's the rate salt in? This I have to think about. So let me look over here. I have got Q cubic meters coming in per minute. So each minute, Q cubic meters of liquid come in. Each of those cubic meters of liquid has C in grams of salt in it. So the product, C in times Q, is how many grams of salt come in per minute. So let me write that a little bit more carefully. Maybe I'll write it on the side here. Or how about on the side here, so you can see the intake portion of the diagram. So I have C in grams per cubic meter, and I'm multiplying that by Q cubic meters of liquid coming in per minute. And I'm saying that that tells me how many grams of salt are coming in per minute. So that's the rate at which salt comes in. So continuing to fill things in here, I have C in times Q. And then I'm supposed to subtract the rate at which the salt leaves. So that should be, let's see, looking at this area, for the same reasoning as before, it's going to be Q times C. C grams in every cubic meter, with Q cubic meters leaving every minute. So C times 2 grams leaving every minute. And there's our law, there's our differential equation that we got from saying that the amount of salt should be conserved. Salt should not be created or destroyed just for not arbitrarily. Now you see there's one unknown function, that's C of T, the concentration in the tank. On the left side here, if you want to write this down as as something that looks more clearly like a differential equation in C, C prime equals and then some stuff involving C and T, then you should take the derivative on the left side. And now if you try to go ahead and take the derivative on the left side, the V is a constant. The V does not depend on time. That's thanks to the fact that we rigged this so that the flow rate Q of fluid coming in and the flow rate Q of fluid going out are equal. So we're guaranteed that V is constant. If we had not done that, and we may change that at some point later in the course, then V would depend on time. If V depends on time, then this derivative here, you would have to compute this using the product rule. Luckily, V is a constant, so I can just pull it out of the derivative. And here I've got V C prime of T equals C in Q, and these are constants here, minus C of T Q. So it's not so different of a differential equation from what we saw with Newton's law of cooling. It's actually a really similar format of differential equation. In fact, just look at this. If I just write it like this, pull out the Q and divide both sides by V and stick a minus sign in front, then I've got C minus C in. Okay, hopefully I didn't make an algebra mistake there, but it looks just like Newton's law of cooling, right? It's just, instead of temperature, it's this concentration. All right, so you can use the same kind of techniques to to solve this, actually.